Okay, so we're going to try an example to illustrate how we use this unit vector notation and how it interacts with what we already know about the magnitude and direction of vectors. Okay? It dovetails really nicely, but this nice simple problem will show us how all the notation works out. All right, so the problem is, just in case you can't read my awful handwriting, is given that an object's position is dictated by that function, right, for position, and that's 3t in the x direction, negative 4t squared in the y direction, and just 2 in the z direction. So in other words, it's the z component of the object's position never changes. So effectively, this is a two-dimensional motion problem because we're kind of free to just say, well, if it never changes in the z, then that's our plane right there. But just so we can see how the whole 3D thing works out. And A asks us to find what is this object's velocity as a function of time. So we'll solve that one down here. And what we do, remember, is to take the time derivative of the position function, dr dt. I'll write it this way, just to hopefully be clear. And when we do that, well, we just need to take the time derivatives of all of these coefficients. Now, 3t is a very simple derivative to take, right? We just end up with that, and the I hat sticks around. The next one is a little trickier, but not really substantively trickier, so you get 8t. And for the last one, you're taking the derivative of a constant, and that just gives you nothing. So I won't even bother to write down the z component, okay? So we've got that. And this function, it has to be equal to the velocity of the object, right? Because the definition of instantaneous velocity for an object is the time derivative of its position. Okay, so A, check, all set. B, and we'll bring that one down right underneath here. Well, now we're just going to evaluate this velocity function at time equal to 2 seconds. That's what that is saying. And so if we do that, we end up with 3. There's no time dependence there for the x component of the velocity. And then we evaluate the y component to be that. And that leaves us with negative 16 meters per second in the negative y direction, right? So if we wanted to make the units clear here, we could say meters per second like that, okay? But yeah, we'll generally be working in standard units. All right, so that's A and B out of the way, nice and quick. And let's bring C over here, where we have just a little more space, all right? It's not super complicated, but a little more space is required. Okay, so find the magnitude and direction of the velocity at this time equal to 2 seconds point. Because obviously the magnitude of the velocity is going to change over time because its position changes over time, and the velocity function that we found is a function of time, at least in terms of the y component of that velocity. All right, now there's a formal way to do this. You'll remember that for the procedure we were looking at for 2D vectors without all of the unit vector notation, we would find the x and y components first. We already have the x and y components here. And then we would take those x and y components, and if we were summing vectors, we'd sum them up. And then we would use the Pythagorean theorem and arctangent to find the magnitude and direction. So because we already have the x and y components here, we can kind of skip right to the end. And the magnitude of the velocity, I'm just going to call it v, so I'll drop the little arrow to represent that this is talking about the magnitude. Technically, like, this is the way you should write a magnitude, but I'll probably flip between the two. And that's going to be equal to the square root of the square of each one of these components, right? So I've done the little bit of algebra to solve for not the magnitude of velocity squared, but just the magnitude of the velocity. And so we take its x component and we square it, take its y component and we square it. And when we do that math, we come out with about 16.3 meters per second. We're not given a lot of sig figs here, so we could conceivably round that considerably, but let me just keep 3 sig figs so you get the idea. All right. So there's the magnitude of this velocity at time equal to 2 seconds. And then we need the direction. So the direction, again, you can kind of blindly just plug it into the equation that we have for this. That's going to be y over x, so negative 16 over positive 3. And that gives you a negative 79.4 degree angle. And there's your answer. Now, it's worth being just a little bit cautious here. Remember that arctan, that function, repeats, okay? And so you can get into funny situations where if you're not keeping track of what the geometry of the situation looks like what the picture of the situation looks like, you might get an angle that doesn't make a whole lot of sense or is measured from an axis that you don't mean. So let's just take a look at what this would look like on an xy coordinate axis, all right? Now remember, we're talking about velocity vectors, but we can graph those out just like any other vector, just like displacements or forces or accelerations or whatever. And so what we've got is an x component that is 3 at time equal to 2. So we'll just call that 3 right there, okay? So that's 3 meters per second in the positive direction. And then the y component, I'm not going to be quite to scale, but I'll come down here a ways. Okay, and this is the negative 16 meters per second that we have there at time equal to 2 seconds. And remember that the magnitude, the full vector that is representing the velocity, x and y components all together, would look something like this. Let me get a different color. Okay, and it's the hypotenuse of that triangle formed by its x and y components. So this is v. And that would be this 16.3 meters per second, and it would have this direction. Now, this direction is measured from the positive x-axis, and remember, normally you start at 0 degrees and you count up going counterclockwise. So if you have a negative angle, then you're going the other direction. And so what we're saying here is that this angle right in here is this 79.4 degrees. And even though I haven't drawn a great picture, we can see that that angle makes a lot of sense. We know that we have a positive x component, a negative y component to this velocity. So the vector has to be down here in the fourth quadrant, and that makes sense corresponding to that angle. So we haven't run into any mathematical oddities along the way in using arctangent. And having a little picture like this is usually a really good idea, halfway between a star and a check mark there, okay? So that's a simple problem that you hopefully can follow right along with. And you've got some other simple problems on your assignment, and there's some other simple problems in your textbook that you should try out if this notation is unfamiliar to you and you're still sort of setting in, because it's pretty standard, runs around a lot in mathematics and physics and engineering, and good to be familiar and be skilled in its use. So thanks for your attention, and I will see you later.